This is Module 6. We're talking about compilation, and we're in the semantic analysis phase of compilation. And this is actually a very long and deep topic. We're only going to take a very shallow dive into that deep pool. Basically, by the time we're done, you'll have an idea of what the different kinds of semantic analysis are. You'll have an idea of the purpose of semantic analysis, and maybe some of the ideas of the limitations. But the goal is not to give you a deep understanding of any specific form of semantic analysis. Those of you that will go on to take SE410, you will do more of this. Any course where you're going to talk about software modeling or software quality assurance, software verification and validation, you may have some more exposure to semantics. Some of that comes about through testing, some of it comes about through semantic analysis of the software. As usual, when we're done, go back to these outcomes and convince yourself that you have these. Okay, the compilation overview that we talked about last week. Here we are in the semantic analysis phase. Last week we talked about lexical and syntactical analysis. Next week we'll talk a little bit about optimization, code generation. So what's the goal of semantic analysis? Remember, the goal of syntactic analysis was to make sure that the program statements were structured correctly. And semantic analysis is about making sure that the program statements are playing together meaningfully. Now, meaning has a very limited context here. Remember, technically, we're saying computation has no inherent meaning. So there are a few kinds of questions that we can ask that are more meaning related than syntax related. And again, we can go back to our general idea of what syntax and semantics means even from natural languages. The syntax is the construction of the sentence, the legal sequence of tokens or terms, and the semantics is what does it mean? Well, for programming, a good notion of what a program means is observable input-output behavior. In terms of program meaning in an individual statement, it's does this statement actually work? Will it when it executes, will an appropriate behavior be executed, or will there be a problem? And we're very limited on what we can ask, but here's some sample questions. Are all the types in a particular statement consistent? If you're assigning to the variable x and x is an integer, do you have an integer value that you can assign to x? Some programming languages require that variables are declared, and some even require that they're declared and initialized before first use. You can ask those statements because you could have a syntactically correct program that did not declare a variable before you tried to use it, but it would not be semantically correct. What effects are the program statement on memory? What does the memory look like at any point in time? What value does a variable hold at any point in time? These kinds of questions. Can a value ever be out of bounds? Can a value ever be undefined? These are good things to know. If you can do analysis and prove that those things don't happen, it can reduce your testing, and it can also improve the provable correctness of the program. What previous statements potentially affect a specific statement? This is a good one. So when you're doing debugging and you know that a particular statement has been, you believe that there's a particular statement that is wrong, well, how did it get wrong? What were the statements prior to that that led up to that? And a very large piece of code, rather than going through the thousands of lines of code, if you have the ability to analyze what previous statements potentially affect the current statement that you're interested in, maybe you're going to only look at dozens of lines of code instead of thousands of lines of code. And you can ask that question in the other direction. If this statement is executed, what future statements are potentially affected? Basically, what do we know to be true of a program at any point? And again, it's the briefest of overviews of this topic. You can spend a long time on this. I've given you quite a few PDF notes that go into a lot more detail on the topic. And the purpose is just for your reading pleasure. You don't have to put yourself on the hook to learn all those topics in detail. They are there for you. If you find that you have an interest in this, it's a good topic to make a mark for yourself in. It's a good niche expertise area. Okay, semantic analysis. Let's do one example of semantic analysis is type analysis. Now, what is a type? A type is a set of values with associated operations, and we always want to make sure that our statements are consistent from a type standpoint. Some programming languages make no check at all. Some programming languages do not require that you declare a type, and they'll keep churning along hoping to make the types work. They actually infer the type based on how you use the variables and terms, and they keep churning along making the types work until they just can't anymore. Other programming languages require that you declare type, but they allow it in such a way that you can still have type errors on execution. Languages like Java are strictly typed. That's the correct term. They are strictly typed, meaning that if you pass type analysis in the compilation phase, you're guaranteed that you will not have a type error in the execution phase. So basic type analysis, x equals foo, well, whatever the type of x is, that function or method foo has to return that same type. It has to match. How do we do it? Well, there's two ways. One is named type checking. So if you have a programming language that relies on declarations, it's pretty straightforward. Hey, you said that x was an integer, and you said that foo returns an integer. We can compare the names. The other form is structural type checking. So now what we're saying is, in terms of, say, memory allocation, do these things match? So in C we have the notion of a struct, and if I had struct 1 defined as int x float y, and I had another one defined as int d float p, well, they're both an integer followed by a float. So in terms of memory allocation and in terms of accessing the elements of those struct, they behave exactly the same. So the idea here with structural type checking is the compiler will examine the structure and then either say yes, these are type consistent or not. Now, object-oriented languages are kind of in between the two, because if you think about it, when you take a generic class and then you extend it so you have a parent class, child class, if you write code for the parent class, you can use the child class in there, and it is type safe, it is correct. Why? Even though they have different names, I have class A and then I have class B extends class A. How can I use class B in a place where class A was called out? Well, that's because class B is remember it's an is-a relationship. Class B is a version of type A. And the idea is, because class B inherited all the attributes and methods of class A, they are structurally equivalent. Now that doesn't mean that the compiler actually has to do the structural analysis because of that clever keyword extends. So once we get the extends in there, that can actually be a form of named type checking. Instead of saying this is the exact name match, I can say a name or a child of the name or a descendant of the name. Some kinds of examples. In this first box, we're wondering what type we can have. Let's see, x equals 10, y equals 12, z equals x plus y. They all have to be the same type. What would work here? Well, depending on the programming language, maybe integer. And what about this 12.0? That's not an integer. Depending on the programming language, it may just truncate. Now, some languages give you an error on that, right? Error, possible lossy conversion. Or some just do a warning, possible lossy conversion from double to int. Others, if you said these were all floats, would take the 10 without the decimal point and say, okay, I'm going to accept that as a float. If you declare in here what the type is, depending on the programming language, you may be able to declare int, you may be able to declare float. You definitely cannot use Boolean or string or char. It depends on the programming language, but that's the kind of analysis that occurs. Now, what if you don't declare? What if you just say, like JavaScript just says var XYZ, but it doesn't define the type? Then the actual execution of the program, in this case it's not a compiler, it's a translator, while it's translating the program, will try to make these types all play together for as long as it can, and then if it gets to a point where it can't, then it will just stop operating. In the next example, we have dog and fish and z equals x plus y, and for many programming languages this is perfectly legal as long as the type that you put here is string. And in that case, x plus y is the plus operator for strings becomes concatenation. For some programming languages that will not work. So for some programming languages like C, if you're going to do string manipulation, string concatenation, you have to use specially defined string functions. You can't just use the plus operator. But Java certainly allows this. Many languages actually allow this. The only one that works there is string. And then if we do this one, okay, now I've got a string and a float, or a string and a double. Boy, that's going to be a tough one. There's no typing scheme that would work here. If you were trying to declare a type, you couldn't. If you were in a language like JavaScript that was inferring the types, it couldn't, and it would stop working. I'm going to go out on a limb. There may be some languages that would actually convert that 12 to a string because X is a string and it's the only way it can make it work. I'm not aware of a language like that right now. And then lastly, type XYZ, and we have user input, user input. Oh, now we're really messed up because we don't know what the user's going to do, right? You can't control the user. You can tell the user to put in an integer, but that doesn't mean they're not going to put in their birth date or their first name. So the idea here is you can do typing, probably string or int or float would all work here, but then you are reliant upon the user. And so the type checking has to occur at runtime in that case. Now, how does Java get away with that? I said Java will not give you a runtime type error. And how does that work? Well, that's because if you remember in Java, when you use the scanner, you actually say, let's pretend we made all of these integers. You actually say next int. If it's doubles, it's next double. It's actually a method that does that. Now, the user can still mess that up, but you get a different kind of error. You get the type mismatch error based on I was asking you for an integer and you gave me a string. Even then in Java you can get around that using try, throw, catch, right? Using the exception handling. So if you're actually programming defensively and correctly, you still would not get a type error in that situation. Okay, I'm going to pause here and I'm going to go through the three basic types of semantic analysis. It's denotational, operational, axiomatic. And that's a separate lecture, so I'm going to pause here and then we'll continue on.